Hey, well, hello and welcome to the first RISC-V workshop. I'm Krste, faculty at Berkeley. We're all really excited. You know, when you throw a party, you never know how many people will show up. Turned out that we actually hit capacity. It was not something we were expecting, so that's great. A lot of exciting stuff been happening at Berkeley, but this is really about building the community, everybody out there. So I'm glad that it's actually about 3/4 non-Berkeley. And over the course of this next day and a half, it's going to be fun to get to know everybody and what you're all doing with RISC-V, or interested in doing a RISC-V. Usually, this is based on a Berkeley retreat model where we do these meetings, but usually we kind of know who the people are attending. We have no clue about half of you, at least who you are or what you're doing. And there's such a large number, normally go around and have you introduce yourself, but there's just too many people to do that. There's some seats up here, if you guys want to sit up here. I think we're going to delay that till the dinner. We'll have a structured dinner to make sure everybody gets to know each other pretty well. Also through the poster previews, you get to see a bunch more of the other people, I think, and what they're trying to do. Okay, so rather than doing a round of introductions, I'm just going to dive straight in. Why are we all here? And clearly we're all here because instruction sets don't matter, right? They really don't matter in the broad sense of performance and energy in a computer system, because when you build a computer, most of the performance energy is from things like algorithms, right? Great instruction set is not going to save you from somebody with a dumb algorithm. Application codes, how people write the code, the compiler they use, OS and runtimes they use, and there's a little impact from the ISA, right? Microarchitecture is a big impact on how well computers run. Circuit design, physical design, all these have a much bigger weight on how well a system performs in the ISA, right? Fabrication process as well, right? So, and this is just the processor of the computer. If you're building an actual system, there's all the other stuff. There's displays, there's radios, DC-DC converters, all that has a much bigger impact on the system than the instruction set. So ISAs don't really matter. So that's why we're here, is because they don't matter, except they kind of do. And why do they matter? Well, they matter because it's the most important interface in a computer system, right? It's where hardware meets software. And you'll find this out if you try and change the ISA, right? Why this is the most important interface, right? It's a massive cost to take all the ISA-dependent parts of a software stack and move it over to a different ISA, right? That's a huge cost, all the ISA-dependent parts of a software stack. What you'll find out, though, it's a massive cost to port all the stuff that's supposed to be ISA independent, because it actually isn't. And so you'll find there's a large cost to recompile, import, and QA all of this stuff as well, right? So changing ISA is a big cost. Another problem is you may not be able to recompile because it's not your code. You bought the code from somebody else, it's compiled with some ISA, you have to go use that. Or you have the code, but you've forgotten or lost the ability to recompile it, right? This is pretty common. You get bit rot in the tool chains, you weren't wise enough to save in a VM or something, you can't rebuild that code anymore. Or what's also quite common, you just lost your code, you have no clue how to rebuild that binary, right? So these are all reasons why it's so expensive to change the ISA. And if you look at building new chips, most of the cost of building a chip is writing the software for it, right? So this is why ISAs do matter, okay? And what's interesting is if you look at most big new chips people developing, they have several ISAs, not just one, but there's one for the application processor, there's maybe one for the DSP, some radio chip, some graphics, image, they may all have different ISAs, right? So that seems like a big mess. If the choice of the ISA doesn't have much impact on computer system performance, right, and it costs a lot to use different ones, why isn't there just one of them? So why isn't there just one industry standard ISA? I think I've just lost the mic up here. Right? That's better. Yeah. So ISAs should be free and open, right? Kind of all agree to that. And historically, ISAs have been proprietary. And this is really just for historical and business reasons. There's no technical reason why an ISA should be proprietary or why the standard one should be proprietary, right? And it's not like an error of omission. It's not like the guys at Intel sort of wake up one day and goes, oh, you know what we forgot to do today? We forgot to open up our ISA. Well, the guys at ARM, the guys in Cambridge, wake up from their night at the pub next day. You know what we forgot to do? We forgot to open up the ISA. No, if you try and do an implementation, there's this joke about the shortest amount of time in the universe is between traffic light turning green and the New York cabbie behind you honking their horn. That's not quite true. It's the time from you putting out an ARM core on the web and getting a letter from an ARM lawyer, right? So it's not an error of omission that the commercial ISAs are not open. And it's not because these guys feel justified because they do all the software development for their ISAs. Clearly, these ISAs, most of the software developed for them that relies on them or that you'd have to do something about if you change the ISA isn't developed by these companies. Intel is a pretty big software company, actually, but it doesn't develop all the software for x86s. ARM doesn't develop all the software for ARM cores, right? And it's not as if they're good at doing it either, right? Yeah, I'll get into that, but it's not the only people who could possibly design a competent ISA. They're definitely not the wonderful ISAs, the ones that are out there, right? And they're not like the only people who can verify ISA compatibility. I mean, an ISA is actually a pretty simple thing compared to most things in the industry. So, making Wi-Fi interoperate is a much bigger challenge than making hardware work on a software obey a given ISA, hardware compatibility there. So, industry knows how to have open standards and how to ensure compatibility between things developed by different groups. Like ISA compatibility is not something that you need, a juggernaut like Intel to ensure that chips work to the same ISA. And one big reason is, one other big worry with proprietary ISAs is they're not guaranteed to last. So no, Dick Seitz is here, so I'll use his favorite ISA as an example. Digital Alpha was a nice, clean RISC architecture design, but for no technical reason, it's disappeared, right? Business decisions, whatever. There's no, a lot of the academic research community built tools around Alpha because it was nice and clean, elegant. You could buy workstations using that Alpha RISC instruction set, but it's gone. And, it also took down VAX when digital went under. So there's no guarantee x86 is going to last, or 360, or ARM, or any of these other ISAs. And a lot of them have died in the last 10 years or become marginalized, right? And what's worse is if you build your toolchain around one of these proprietary ISAs, even if you wanted to keep going with Alpha or one of these other dead ISAs, you would find that there would be probably some small IP holding company who has some of the rights in some form who would come after you, right? There's some legal entanglement there. So even if you wanted to, you couldn't keep these things alive, right? So we want a viable, really open ISA. And the reason we think this is a good thing, I'm sure many of you agree, there should be greater innovation. If we have lots of people working on the same ISA spec, both proprietary cores and open source cores, there's going to be a lot of innovation. We can try a lot of ideas. You don't have to wait for the company to agree to grudgingly add the thing you want. You can go try it out yourself if it'll help your application. In the open source space, we can share core designs. That means hopefully we get higher quality designs. More people looking at, is that really a good idea for your branch predictor there, or your vector unit? I want to add this other widget in, and I'll make it better. The more people looking at the same design, we should be able to raise the quality of it. Also, if you're interested in a security angle, being able to see the code for the processor you're putting down is kind of important to quite a few entities, such as foreign governments, who don't want to trust a foreign-owned company, obfuscated bit of RTL they have no clue what's in there. And sort of 5 years ago, you'd have been, people wouldn't have worried about this, but recently, given all the exposures of what actually goes on, it's a valid concern, right? So you want to be able to see the code that you're putting on your chip. Also, I think actually the cost of licensing these cores is not the biggest reason to do an open ISA, but it is a factor for some small, low-margin parts. Right? The actual cost of licensing, and perhaps more importantly, the time it takes to negotiate a license is also a limiter. You want this, if you want a core, just go use it. You don't have to wait to negotiate a contract with a big company. And this thing about longevity, you would like, if you're going to start embedding devices in concrete, you want to be able to make sure those tools keep working 50 years into the future, right? And so, this kind of timescale, the lifetimes of these big companies is just too short, right? And for us, the actual original motivation was making architecture, education, and research more real. So with fully open hardware and software stacks, and actually hoping to get these out into commercial use, we can actually teach students how to make systems better using the systems people actually use out there in industry. So close that cycle instead of having toy systems and then have to learn how the ugly real systems out there work and work on those. If we could make all the systems better and the same, it would sort of remove a lot of hassle. And so Dave could write his textbook in much shorter time than it takes him right now to digest the ARM manual, right? Okay, so we all agree this is a great idea. So what style of ISA should you use? Well, if it doesn't really matter, then you should pick one that's easy to implement and efficient, right? If it doesn't really matter which ISA, so pick an easy one. You know, and Seymour Cray, he had some good ideas way back when. So going back, you know, more than 50 years now, the idea of a load store ISA, it's a great idea, and it survived. You know, it was refined by the research, you know, 30 years ago. Dave, the guys at Stanford and IBM, you know, they did a lot of work in pushing this and the compiler technology. It's still a good choice, and it's basically survived this 50-odd years of development. So there's no reason not to do a RISC. People say, well, are you really, you guys are architecture researchers, are you really saying that nothing has happened over the last 50 years? We kind of are. So one thing is, you know, these load store ISAs, people keep saying, well, Moore's law innovation, or how are you going to track that? Well, load store ISAs predate Moore's law, okay? Reality check, right? Moore wrote his paper in '65. Load store ISAs were before that, okay? So all the way through all this Moore's law scaling, this has remained a good idea, right? This basic style of ISA. Along the way, people tried lots of other things, because you've got to do something if you're an architecture researcher, right? Or trying to raise money. The SIS stuff. Well, this actually made sense technologically when you had different technologies for microcode ROM, logic gates, and core memory. But once you're using the same transistor technology for all of those, it doesn't really make sense. So SIS doesn't really make any sense. Stack machines, yeah, once we learned how to build compilers, those didn't seem to be a good idea anymore. VLIW, once you figure out that dynamic predictors have got really good, you don't really want to do static scheduling, at least for general purpose code. It doesn't make any sense. And what's interesting to us after doing the RISC-V thing is industry's kind of reconverged on a refined version of those earlier RISC machines. So, you know, things that are a bit different than MIPS and, you know, Spark of that era. There's things that we do differently now. But what's curious is ARM v8, MIPS R6, both of these have, you know, some of the similar small tweaks that happened from that first generation of RISCs. So there seems to be convergence. Now, having said this, this is for sort of base general purpose software development. The only way forward seems to be for performance improvements is to look at more specialized accelerators. And given that CMOS is kind of stalling and Moore's law is finally, you know, coming to an end in terms of the cost per transistor, you know, people are looking at more specialized accelerators. So really the ISA innovation is going to be more in this space of specialized accelerators rather than small tweaks to sequential ISAs, right? Again, this is an old idea. So you go back to Estrin's paper from the 1960 about fixed plus variable computers. I think this was Dave's advisor. So Dave's advisor wrote this paper about doing specialized accelerators back in 1960. Oh yeah, and GPUs are just a bad version of Cray vectors. So we'll get to that, right? So we're not the only people thinking about this, and some of you I know are involved with these other projects. So there's been other open ISAs. So Spark, to give them credit, back in 94, actually made Spark V8 an IEEE standard, an open standard. You could, I think it was $99, you could get a license to use the Spark ISA. And there's open cores available from Geisler Research. But now this ISA is owned by Oracle. So, you know, V9 and above, it's not clear whether you can do anything with it. This is now Larry's ISA. So OpenRISC is something we're very well aware of. When we started the RISC-V project, we looked at it pretty carefully. There's some people from the project here. When we started, the 64-bit thing wasn't there at all. And what's interesting, apparently this was a bunch of Slovenian undergraduates typing in Dave's DLX educational core into Verilog and turning that into a core. So, you know, is that project there? Shumpe is here from Open Processor Foundation, and he was involved with the SH architecture from Hitachi, and that's, you know, patents are expiring. This is now being opened up. I know there's people here from Lattice as well. So the LM32 core is another popular soft core that's out there. So these are interesting. They're all RISC ISAs, right? So why do we do RISC-V? Well, this is back in 2010. You know, I've done a lot of research projects in architecture, and every time, new group of students, new set of projects start up. One of the big questions is, which ISA should you use? And the old joke is, the only two mistakes you can make are design your own processor or use somebody else's, right? Those are the two big mistakes. So the obvious choices in terms of getting software and everything else up are x86 and ARM. Well, x86 is just impossible. Really impossible. Every time I have fantasies about implementing this, I sort of crack open the instruction set manual, and the first instruction is AAA, right, alphabetically. So what is AAA? It's ASCII adjust after addition, right? Obviously a very important instruction. So what this instruction does, right, the AO register is both the source and the destination. It's hardwired in. If the null nibble is greater than 9 in decimal, or the auxiliary carry flag is set, then add 6 to the low nibble, discard the overflow, increment the high byte, set the carry flag and auxiliary flag, right? Otherwise, just clear the carry flags. Okay. So this is obviously such an important instruction to have in the ISA that you give it a 1-byte encoding. I couldn't make this up. Right? So these are the guys we're trusting with the most important interface in the computer system. Right? I think we actually dropped this in x64, thankfully. But still, every time I go and implement the manual, this is great, because this is like, here be dragons. I open the first page, this is there, stops me thinking any further about touching x86. Okay, well, ARM is the other option, and ARM is a RISC core, right? So if you look at ARM, you realize that's just mostly impossible, to paraphrase Doug Adams, right? It's also incredibly complicated for a RISC core. How can you read all those papers from Berkeley and then come up with the original ARM ISA? I don't know. Something to do with pubs in Cambridge, I think. So this is really complex and also has major IP issues if you try and implement it. And ARM v8 is a much cleaner ISA, but happens to include v7 if you want to make a compatible implementation. So it's incredibly complicated. I think it's like 5,000 to 6,000 pages of ISA manual for that beast, okay? So we decided we're not going to do that. So we started a 3-month project the summer of 2010 to develop our own clean slate ISA. So may as well start from scratch. So 4 years later, we released the frozen base user specification. But this wasn't like we just sat in a room writing a spec. Along the way, we did a whole bunch of silicon implementations, and you'll see some of those in the demo sessions later this evening, and wrote a bunch of publications using it. So we had a lot of experience as we went through this and iterated a few times on the ISA spec. So we finally froze it, and then this summer is when we actually did this big PR push, which is probably how most of you heard about it, as we started saying, well, this seems to be something people want to use, and we found out people were actually grabbing it from Berkeley and using it. So we started to make a more serious push on this. So here we are now in 2015. So having started as an ISA, I wanted for our research projects to use in education. The goal now in 2015 is a little bit more ambitious, right? So our goal now is basically to become industry standard ISA for all computing devices, right? That's what we want to do. I wouldn't have said this a year ago, but the more I think about it, this is pretty much what I think will happen. And why do we believe this? But if you look at what happened to Linux, Linux used to be this oddball thing. There was always proprietary Unices out there. And obviously you wanted to use, Solaris, you wanted to use AX. Nobody wanted to use HPUX, but that was there. Or Digital Unix or True Unix. There's all these proprietary Unices out there. And they got killed because Linux is the advantage of open source, lots of people looking at it, cleaning up the design, putting over time, adding in all the best features that were in all those other operating systems, right? And it just has taken over now. There may be a few people out there, a few holdouts with proprietary Unices, but basically Linux is the thing you expect to use if you're running any large system. And all the handhelds are based on that, the Android's based on that. So it's kind of swept over. So that's what we expect to happen with RISC-V, right? I think we're at the point now, I don't think we can stop this happening even if we wanted to, right? So what's the most effective way of making this happen is part of what this workshop's, you're at the beginning here, so a little bit into the beginning of this actually happening, right? So how are we going to make this happen? So something is that, RISC-V, one confusion people have is RISC-V is not an open source processor, right? That's not what RISC-V is. RISC-V is a specification. It's just a contract between hardware and software. It's just the ISA. Now at Berkeley, we also happen to have open source RISC-V implementations that you can use. But the goal in the RISC-V project is to enable companies to do proprietary implementations also. So this is not some kind of GNU thing where you have to reveal all your RTL to us. We just want to standardize that interface so the software guys can rely on stuff working, the hardware guys can compete on the quality of their implementations, and we hope the open source versions are actually very competitive too, because we'd like to use those in education. But we're not trying to restrict in any way, so we want to encourage open source and proprietary implementations of this ISA. Okay, so it's not an open source processor per se. It should enable open source processors, but that's not it. It's an ISA specification. And as we get into this, we'll talk a bit more about this through the workshop, you kind of realize the ISA is a place to start, but you really need to start expanding out the spec to cover how should you build SoCs. So people talk about the ARM ecosystem, and what's really happened there is over time they figured out this is how you build an SoC the ARM way. There's all these components in there, and this mind share builds up. We kind of need to work on that too and expand the spec out a bit. And in particular, we've been thinking hard about the accelerator piece, because one of our research project, the Aspire retreat that just finished before you guys came in here, is all about specialized engines and accelerators. And we've been thinking about how to do that cleanly and well. And so I think we have a particular advantage in having done many iterations of that, of how to do that. So we want to define how that should happen for future SoCs as well. This is one of the big things, most of the cost is in software, so I want to make sure software can be used across many chip designs. So I think the real key here is not open source hardware, it's hardware that can run open source software. So most of the thing you want to do with your hardware is enable it to run all that software out there, because that's where most of the cost is. So build chips in the way you put the specs out so the community builds all the software you need to build your chips. You don't have to roll all your own every time you build a new chip, right? So the goal is build platforms that can run software, open source software. Okay, so kind of giving the goals motivation, I'll sort of do a quick summary of what RISC-V is, and along the way give you some of the philosophy. There's a lot of questions about why do we do this way and that way. I'll try and give you how we're thinking to help you understand where we're coming from. So one thing, so the base was meant to be extremely simple. So the base is the base integer ISA, and there's 3 variants of that: RV32, RV64, RV128, corresponding to the address space width in the processor. What's nice about these base integer ISA, you only need to implement 40 hardware instructions, and that's enough to run compile toolchain, operating system, linker, everything else, right? And the goal is that this is always supported. So anytime in the future you need a core, you can just implement 40 instructions and have working C compilers and maybe OSs and everything else, right? That's one of the explicit goals. Keep the simple baseline very simple. As educators, this is incredibly valuable. We can teach people the whole thing, in a lecture or two. And it's actually something that's competitive with those complex beasts that are out there in terms of ISA complexity. People ask us, why did you do 128-bit? Well, when we first did this, it was kind of a joke in the manual, because there is this saying about the only thing that kills an ISA is running out of address bits. Another part of the Aspire project is looking at data center systems, and the move to solid-state storage in the data centers means that already people are running 10 petabytes of solid-state storage in some of these warehouse clusters. So 10 petabytes already puts you up into 50-something bits. A few more decades of doubling, less than a decade of a few more doublings of NVM technology, we're going to run out of bits. If you actually want to address that, have the identifiers used to address that storage fit into machine register. So 128 bits is actually not that ridiculous, and we already have the ISA, and you know what? The base ISA is only 40 instructions, right, to do that. It's very simple. Now, on top of that, we have the standard extensions. So integer multiply divide, atomic ops, single precision float, double precision float. And G is just the shorthand way we say of combining the base ones, IMAFD. We view this as a pretty good general purpose ISA for most software development. So if your main goal is I just need a core that runs software, most software, this would be enough, we think, to run most software. Now, this is the part that's frozen. This is what we froze in last year. And this piece, the base, is designed to be a fairly standard RISC encoding in a fixed 32-bit instruction format. right? So this base instruction set, your core that you implement only has to deal with fixed width 32-bit instructions, just like a classic RISC machine. Here's the formats. They're pretty vanilla. You have 32 integer registers with a 0 register. We made care to make it very simple. All the register fields are in the same place. RD is in the same place, RS1, RS2, in all the instruction formats. It's very simple. Part of the design is to make it very simple but work really well. So it actually, we don't see any difference with all the other more complex integer ISAs in terms of performance. There's a few things you could imagine adding that might help a few application domains, but one of the goals is to separate out the stuff that you really need for everything from the stuff that helps a subset of applications. And the goal is you don't mandate adding instructions for an application that doesn't need them. One of the goals expressly is to be the base of accelerators and customized engines. And so this base 40 instructions is meant to be enough that you can get the full compiler up and running, and then you can mutate it any way you want to add specialized engines and widgets. But starting from something with a completely functioning tool chain, right? It's already there. That's the minimum set you need. For example, like a bit operation, a bit set extract. You might imagine I want to add those. Yeah, it only really helps a few subset of applications. You don't want to mandate that so somebody who's building an accelerator has to build that in. If they have a whole accelerator dedicated to doing bit stream manipulation, then they still have to go implement this funky little bit thing you added. So keep the base ISA extremely lean, but good enough to run the entire software stack, and reasonably efficient at running it as well. So AMOs, 2 categories here. You add this if you're doing any kind of multiprocessor stuff or running an operating system. Fetch and add style AMOs plus row reserve store conditional. This is a place where multi-word atomics is something that's still, in my mind, a research thing. It's not clear what to do there. So these are also single-word atomics. One thing we did is, on the basis of feedback, is add, luckily the language guys seem to have agreed on a language-level thread memory model. And so we've added acquire release bits on the AMOs, so you can get release consistency very easily from these instructions. So that's some sort of bit of innovation there in the ISA design. Okay, so that's just the highlights of a few pieces of the ISA. So one thing I want to talk about is this thing about why do SoCs have so many ISAs for all these different kind of engines and widgets. I think the real reason is the IP comes from different places, each with proprietary ISAs. The managers are not good enough at stopping the engineers from doing their own cores, so they have these homegrown ISA cores they have to support. And I think this is part of the reason there's such a high cost for developing new hardware around the industry is the commercial, the processors you can get out there are not a good base for an accelerator. So you don't want to use an ARM core as the base for an accelerator. It's just too big and ugly. That's not what you want to use as the base of an accelerator, so you want to use something else. And what is that something else? Well, it might be a Tensor core or an ARC core, or it might be you decide you're going to home grow that thing, and then you have to write all the software stack and support it. And what you find out, you actually, every core needs a C compiler. That's kind of one of the facts of life. And it's non-trivial to build and support that. So, design one ISA to rule them all. That's kind of the goal here. Get rid of all this. One thing we did that's different than conventional RISC is we supported variable length encoding, and this is built into the basic design. So the base ISA instructions are 32 bits long, but they reserve, the bottom 2 bits are set to 1-1 in a 32-bit encoding. And if they're not 1-1, then it's a 16-bit instruction. So we have a compressed instruction format. It just fits in. You just add it on top of the 32-bit encoding. When you add that in, now the original 32-bit instructions can be arbitrarily 16-bit aligned, right? If you don't add the compressed, they only have to be 32-bit aligned. But now they're allowed to be 16-bit aligned when you add compressed. So compare this to the way ARM did Thumb, right? So what ARM did with Thumb is they had a 32-bit base ISA. Sometime later, they decided they want to do compressed instructions. So Thumb 1 added a separate fixed 16-bit instruction set that was different than the 32-bit instruction set. So a completely different ISA, right, but compressed. But you could branch between the two, jump between the two ISAs. They realized that, well, that you suffer in performance. You end up needing more instructions if you only have 16-bit. So then they decided Thumb 2. So Thumb 2 has both 16-bit and 32-bit mixed. The 16-bit is different than the Thumb 1 16-bit, and the 32-bit is different than the ARM 32-bit. So these are the guys we trust with the most important interface in the computing system, right? So, no reason to do that. Anyway, so our compressor is much cleaner, it's modular, it fits in. If you need it, you add it. If you don't need it, you don't pay the cost in the implementation. You can just stick with fixed 32-bit width. And then we support larger extensions going on. So the only cost we really have in the base ISA is that branches and jumps are at 16-bit granularity, so we lose 1 bit of reach compared to what you have with a conventional RISC ISA. So we have put out a draft of the compressed ISA. We have a new draft we're going to release soon that's cleaned up from Andrew's master's thesis. But this is quite far along in being prepared. One of the things we want to do this workshop is we sort of limited bandwidth in getting information out and give you a better idea of where we are, what we're currently doing, what's almost there versus what's we'd really like help with getting out there. And in that same category, the RISC-V privilege spec, this mythical unicorn that some of you are bugging me continually about when is this ever going to be released. This is actually harder than the user spec. There's a lot more to think about. One of the goals is to really clean things up. In talking to people building OSs for SoCs and things, we want to really make this a lot easier. And also for our own use, we actually have some of the most complex needs because we build test chips on test chip setups, we build FPGA versions, we have many funky research platforms that we'd like to run OSs on. And so a very high level goal here is for the Unix style OS, we want to have a single port for any RISC-V system. So just one version of the binary for the OS that runs anywhere. It will dynamically figure out which devices are there, but basically don't hardwire in any platform details into the Unix port. So there's just a single Unix runs everywhere. So how are we getting there? So some terminology. So in these diagrams, the black boxes are interfaces and the white boxes are things, instances of things. And we want to provide a clean split between layers of the software stack. So we talk about an application talks to an application execution environment through an ABI. This is standard industry terminology. ABI is what you code an app to. The application execution environment might be an operating system, might be some setup you have on a test chip or a research simulator, it might be purely emulated environment, whatever. It's something that understands that ABI and can provide it. Similarly, for the operating system, we're going to put the OS into, it's going to run talking to the supervisor execution environment through an SBI, which is the supervisor binary interface. It's kind of a superset of the user API, as well as different than the user API. It has things like, I want to interrupt that core, go tell that core to take an interrupt. But the idea is that that SEE can be implemented in many different ways, directly on top of the hardware. You may have a hypervisor, or you may be translating through to some different host operating system or whatever, or a virtual machine. So very cleanly divide that up. And so that our OS only knows about 2 kinds of interrupt. That's all, right? That's it. It doesn't know about devices. Those are handled over so effectively, if you know about para-virtualization, it's like our OS is always para-virtualized. So it isn't really para-virtualized because there's no other thing. It's always running in this more abstracted way, communicating with the system. We do the same thing down with the hypervisor. Now at the bottom, it can't be turtles all the way down. So down at the bottom, we do have a hardware abstraction layer that is how you sort of build up from the real hardware up to providing some of these interfaces. And this is, it has some of the same functionality as PAL code from alpha days. It kind of gives you a way of putting in things that might live in microcode, but you just do them as regular instructions. But also it can hide things about devices or implement devices in this level that communicate back to the OS, right? So we want to really clean up the model in the privilege space. Okay. So initially we're really focused on running current populated operating systems, primarily Linux, in very standard paged environments, but our focus is more on doing it in this clean way to just get going. But the hope is it'll enable people to come up with different privileged environments. And the guys at Cambridge are working on something with capabilities. And I think actually there may be more different supervisor level, completely different options there than there are at user level. But that's okay, because most of the effort is in bringing up the user level code and applications, right? So a lot of innovation may be possible down here. Where's the draft spec? We've been kind of busy, but it's coming out slowly. So very, very soon. And one thing to realize is, if you start, we're not ready to freeze this. We really, we have a version we built Linux for. It's, pretty vanilla what you might, what an undergraduate after taking our classes may construct for a supervisor state. So this next one, we want to involve people in feedback in refining it. So, baking into your chip, you're going to have to cope with things changing in the next I don't know, 6 months or so, right? So it's not quite ready to be frozen. We haven't even got the draft out. We want comments back on the draft. We'll probably have implementations up very quickly. Like as soon as we release the draft, we'll pretty much have the implementations out with the ports. But we want to get feedback on, is this the right thing to do, right? There's a lot of stuff in our ecosystem, and there's later talks today. I won't go over these now. All the compiler tool chain, the operating system, the different implementations. Another talk will cover all the chip generator. So we released our open source Rocket chip generator, which is something that can generate a multi-core RISC-V system. You'll see what's in there. It's written in a new hardware description language called Chisel we developed here. Jonathan will tell you about Chisel as well tomorrow in the bootcamp. And later today, you'll see the silicon. We have 45 nanometer, 28 nanometer silicon implementations out running Linux out there you can take a look at. So there's a lot of stuff we've developed. There's a lot of posters. You'll see the poster previews later today. And the posters out there with some of the research projects using RISC-V. And there's out-of-order cores. There's multi-cores. There's lots of other stuff going on with RISC-V. You get to see those in the posters later today. And also, we'll see posters from the other attendees. I'm kind of excited to see what everybody's been doing with it. So the goals of this workshop really are start building this wider RISC-V community, find the needs, what actually needs to get done, who's going to do it, figure out a structure to manage future RISC-V development. We want this, it's going to be long-lived, so what's the right organization to manage that? We've been talking about a foundation, but we don't know that's the right thing, or what structure a foundation should have to ensure this lasts for a long time. Importantly, when's the next event going to be? On what format? Where should it be? What format? We're looking for input on that. So we'll look for this later after you've gone through the kind of Berkeley retreat experience today and tomorrow. And so the workshop sort of formally ends tomorrow morning, mid-morning, but then we switch into the boot camp where the students are ready to give tutorials on how to use the stuff we already have and sort of hold your hands going through getting stuff going for the first time on your laptop. So an important thing to tell you now is that Albert, who's there, he's missed a VM image, so he put all the tools on the flash drive. You should be trying to install this now if you want to run this tomorrow. And so over the course of the day, in the evening, if you're having troubles getting that going, you should speak to Albert. We'd like you to do that before we start the boot camp tomorrow, right? So the whole world is on that USB flash drive. And there's a lot of things we know are needed, and some of these we're working on. So a formal ISA spec is great. There's, it's just an English document. There's ambiguities. You'll see that on the mailing list. There's some. We need to do that more formally, including the memory model. We have some interest in people doing that. We'd like to push on that. The privileged ISA spec, like I said, is coming out. The compressed ISA spec is also pretty much there, is coming out. One big advantage I think we have over the other ISAs is vector ISA design. Again, Seymour Cray kind of figured a lot of this out a long time ago. People messed it up in the meantime. Now I think people are realizing he actually knew what he was doing. But we've added a lot of stuff on top of that. But actually having a sane vector unit design with compiler support is something we're very actively working on, and we'll put out there as a standard too. A JVM is something we've started working on. We'd like more help. I think we may get some help from Oracle and people to help with that. We'd like to have a JVM. A lot more debugging tracing support for embedded design. We know that's needed. That's one of the big benefits of the ARM environment. I think we can actually do a better job than ARM does here and make it open, so people can write their own open debugging tools on top of a low-level transport API. There's a lot of work going in different kinds of I/O nodes. I know the Cambridge guys, low-risk people of their minions. We've been working on I/O nodes as well. Better test suites are needed. We have some tools we need a lot better here. So there's a lot of there's things we know we need. There's a lot of the stuff that you probably have we don't know that we should be doing. I'd love to get your input on this and what are the priorities. So the workshop format is kind of adopted from the Berkeley retreat model. We've tuned the Berkeley retreat model over many years, but this is a different thing. This is this is a wider community. Most of you are not giving us any money, whereas we usually address our sponsors in these meetings. But what we'll have is a bunch of reasonably short talks and a whole slew of 3-minute poster previews, and we're very strict about keeping you to 3 minutes. And you can actually say a lot in 3 minutes if you practice and do it well. At the dinner table this evening, you don't just get to sit around and talk. You're going to get work to do, and the primary work is going to be we've decided what we're going to do is try and learn as high a bandwidth interface between all of you and Berkeley as possible. So we're going to spread you all out among the tables, so no two people from the same organization outside Berkeley sitting on the same table. There may be one or two Berkeley students on each table. They'll act as scribes. They want to get input from you about what you're doing, what you're interested in, what your priority. Just get a sense of what you want to have happen at RISC-V. We're going to, they're going to report back to me. I'll summarize that the next day, tomorrow morning, and then we'll have a group discussion about what to do next in terms of RISC-V. So we're trying to do this high bandwidth brain dump from all of you to all of us over dinner. But one thing I should say, we do have 2 half-hour breaks before then, so there's plenty of time to mingle and network. But then also at the poster session, you have plenty of time to go around and talk to different people. Yeah, and we have a bar, so plenty of lubricated discussions as well going on into the evening, right? And then tomorrow we'll come back, do the summary of the breakouts, and have a group discussion. Sorry? Yeah. Okay, and then we'll stop the workshop piece and then do the boot camp piece. But before we end the workshop piece, we'll all do a group photo, which will be outside over on the stairs over there for the first RISC-V workshop. And then we'll go into the boot camp. And during the boot camp, there'll be the tutorials, and you can step through those in real time. The students will be there to help with problems as getting the tools running. Also in the afternoon from 3 to 5, there's kind of an open lab time where you can keep working on the labs and have people help. Or we'll be around just to talk to people about RISC-V as well. So there'll be plenty of time over the next day and a half to interact with us and learn about, and just find out what's going on. Okay, so I just want to acknowledge that this is a Berkeley project. It's been funded by a lot of people. So acknowledge all the different agencies and companies that have helped us along the way. We're only really managed to do this because of all this support. Okay, so a few minutes, questions. Nobody's actually working on it. We've spoken to people who may be interested in starting to work on it, but nobody's working on it. Yeah, one thing is to figure out organizationally, how do we get people to know, avoid duplication or team up in the right way? That's something we'd like to understand how to do organizationally. Yeah, all right. Okay, so I'm happy that we have actually 2 groups from outside Berkeley who've been doing a lot with RISC-V. So next up we have Neil from IIT Madras.